All right. We are going to look at the rolling disc as it rolls down a ramp one more time. Um, since though we have covered 99% of what I would like to teach you about the rolling down the ramp problems, I am yet to describe to you how we would go about determining the linear acceleration of, let's say, a solid disk, which is also referred to as a solid cylinder. Usually, when they're longer and taller, we call them cylinders. Usually, when they're thinner, like this hockey puck shaped thing, we call it a disc. Notice again, it's the same thing as a pulley, same shape. You'd use the solid disc to approximate the pulley. Um, Nonetheless, if we were to roll this down an incline, like we did in class, put it on a ramp and just let it roll, um, how would we theoretically predict the linear acceleration that it experienced in terms of its linear gain in speed per second rate, acceleration, right, as it rolls? Well, that's what we're going to talk about. That's what we're going to tackle. Linear acceleration of a solid disk rolling down a ramp, just as an example. Certainly not going to do it for all the different objects, but at least just seeing the process, I think, is worth it. Linear acceleration of a solid disk rolling down a ramp. Okay, so let's draw our ramp. And let's assume that it's a 30-degree angle. What I'm 30-degree angle. All right, and we're going to imagine again, there has to be some friction here because it wouldn't roll otherwise. And remember, if there is no friction, then even a ball or disc or any rollable object would not roll. It would just slide down the ramp. It's only the effect of friction that creates the torque necessary for it to roll. Remembering that gravitational force does not get torque. Gravitational force can be thought of as acting on the center of mass. And since the center of mass, not sure why this continues doing that. And since the center of mass is in the center, of course, and that's where the gravity force is pulling, and that is the axis of rotation, then there's no distance from the axis of rotation to where the force is applied, which is at the center of mass, because the center of mass is on the axis of rotation, and r would be 0. And since torque is r times f, r is 0, torque 0. No torque due to gravitation. Just a quick reminder there. So our goal, again, is to figure out if we can create a formula, a corrective formula. I know I showed you in another class something that was a quick way of, well, not super quick, but it's probably a little more quicker than, shorter in time than this attempt that I'm going to show you to get to gauge a ranking order for the disk versus the hoop versus the sphere. But I had commented that it wasn't actually a correct result. So let me show you how to do that. So here is our disk. Has some physical thickness to it. It has some radius, right? It's going to roll. We know that there's the frictional force here acting along that bottom where it connects and contacts the ramp due to the normal force between the disk and the ramp. So what we have to do is we actually have to do this using two systems, the linear system and the rotational system, as though we are using a system of equations, one from each of these domains, and then combining them in a substitution elimination sort of way to eliminate something that's rotational and replace it with something that's linear, because our goal is to get an A equals. We're talking linear acceleration again, the same linear acceleration that a block experiences as it slides down a ramp. So we have to model using Newton's second law. Right? So we'd say that the net force equals ma. We need to remember that for the linear scenario, the force that's pulling it down the ramp is Fgx. And Fgx is mg sine theta. Something you definitely need to kind of store it. It's one of those things. Store it to memory. Gravitational force down a ramp is mg sine theta. And right now we're ignoring the rolling portion. We're just looking at the idea that we know this thing is moving in a linear fashion. We know it does that because gravity actually pulls it down the ramp. And we're modeling this as though we were modeling it as though it was a block sliding down the ramp. We're not going to forget about friction, because friction, of course, is acting in the direction opposite to its motion, which is up the ramp. If we were asked to draw a free body diagram, which you would have to we wouldn't actually show FGX. I'm just reminding you, you'd actually show FG, which is straight down. You're not supposed to show components on free body diagrams. FG is straight down. The normal force is perpendicular to the ramp, because normal force is always perpendicular to the surface, and the friction force is in the upwards direction. Right? But the frictional force, this is going to be equal to the coefficient of friction. In fact, I'm going to back that up. I'm not going to do that. Let's just reference it as the frictional force. That might be all we need to do. Let me see if we can back that up. I'm just going to delete this, erase this. So I'm going to just reference the frictional force as FF. Okay, so remember that we're looking at motion down the incline. Also remember that the XY axis goes like this. We skew our axes. And therefore, our x-axis is parallel to the incline, and therefore, that's why we call this FGX, because it's in the direction parallel to the ramp's surface along the x-axis. So we end up having F, so this would really have an X here to indicate x-axis motion. That's what I'm looking at. So we'd end up with FGX minus the frictional force equals ma. Right? In for FGX, I'd end up writing mg sine theta, as we had right there on the left. So in here, I would put mg sine theta minus the friction force equals times a. Now, at that point, we would just stop and say that that's kind of one of our formulas that models the net force, remembering that the whole left side of the equation represents the difference in those two forces. Presumably, mg sine theta is greater. Not presumably, it has to be, if it's going down the ramp, right? Mg sine theta has to be greater than the upward frictional force. And the difference in between those is called the net force. So this is modeling the idea that the net force is equal to ma. It's modeling, again, where we started, F net equals ma. So that's what we would call equation 1. Then when we turn to the rotational aspect of this problem, we would then try to model this. I don't know why I said model. We would try to model this using the similar formula we use for rotation. It's also Newton's second law for rotation. At this point, you know that. Remembering that in this case, we would write torque as R times the friction force. Because remember that R in my picture, R goes down like this. This is R, and then the ramp goes like this, and the friction force is like that, right? So the torque created by friction is the frictional force times R. So there's and I'm not bothering with writing it as mu mg cos theta. And I know that because I had left just the frictional force expressed as simply FF over here. So I'm gonna do that because that's actually going to be the thing that I substitute away. So it's not necessary to continue expressing it with more detail. I'm going to leave it as FF. Right, this is again the torque due to friction equals. Now we would have, since we're talking about a disk, the rotational inertia of a disk formula is 1/2 mass of the disk times r squared. 1/2 mr squared. Sorry, it's a little messy. I disk equals, I'm just going to write it as mr squared over 2 instead of writing 1/2 in the front. So that's something that we just bring forward into this problem, something that we just borrow from physics, that we're assuming that that's something that's given. So in for the disk, in for I, I'm going to place it in there. And I might as well make this r look the same, since one was lowercase and one was uppercase. They should all be the same. Both all represent the radius of the disk. Right? So now what my goal is to solve this for FF and stick it back into my linear equation for FF. So let's see what we get. When I multiply by, actually, I think here. Is this, oh, yeah, I was saying there must have been something else I'm forgetting. Yeah. So in for alpha, the other thing we have to do is use this A equals R alpha formula again. This is like the linkage. It links motion. It allows you to connect something that's moving in both a linear and rotational way, and it lets you express one in terms of the other. The connection between the two worlds of rotation and linear motion. So I'm now going to write alpha equals A over R and just plug that in for alpha. Because again, my goal is essentially to start in the rotation world, rid myself of anything that's rotational, because what is our ultimate goal? To determine a linear expression for the linear acceleration of this thing as it goes down the ramp. So that means even though I start in the world of rotation with Newton's second law for rotation, my goal is to kind of undo any of the rotational stuff that's in there. I did that with torque by expressing it in terms of FF, since I know the frictional force lives in the other world too, in the linear world. It's right in the middle there, FF. And now I'm undoing the alpha because I can express it as A over R, right? That's the idea. That's what I'm doing here. So I'm going to erase alpha and put A over R. Now I see that if I were to multiply both sides by 1 over R, or think of just dividing the left side by R and dividing by the right side by R. Dividing the left side by R, kind of running out of space over here, would cancel these R's. And dividing by is the same thing as multiplying by 1 over R, right? That means this R squared would cancel with the 2 R squareds that are underneath in the denominator. I'm sorry that this is like this. Sorry that this is in the way. Something around it. So what I'm now doing is I'm solving for A. Solving for A. And there it is right there. Oop, I need to erase you. There's our linear accelerator. So we're going to notice that everything on the right side is mostly gone other than the m and the 2. And on the left side, I just have the frictional force left. I end up with m, which is here, A, which I'm pointing to with my arrow, divided by 2. Right? So that means when I come back into my world of the linear motion on the left, I can actually remove my FF expression, which is FGX minus FF right in the middle of the screen, and put MA over 2 there. Now, let me pull up the page. Oops. So at this point, this is what I had. I had this from the linear modeling that I was doing, and I have this from the rotation. Again, noticing that I started with something that was rotational, Newton's second law, and now I'm actually I'm taking a piece of it that I know is connected between the two worlds, since the frictional force exists in both worlds technically, and I'm expressing that piece and sticking it into my other one here to ultimately remove the force of friction. Eliminate by substitution, I suppose, is what an algebra book would call that, I believe. Mg sine theta minus ma over 2. Yeah, this is the friction force, and I'm just sticking it, equals ma. And now my goal would be to solve for a. Doesn't look too bad. Also know that if I divide all of my things by m, and I'm allowed to remember do anything I want to a formula, as long as I do it to all parts of the formula. If I paint the left side red, then I have to paint the right side red, because red equals red. In this case, I'm going to divide this term by m. I'm going to divide this term and this term by m. Usually I don't bother doing that. I am this time for some reason. At least I don't bother drawing those, and I just cross them out. But that's why. Right. So now I have g sine theta, which I recognize as an acceleration term, because g is meters per second squared. Sine theta is unitless, just a decimal between 0 and 1, dependent on the ramp angle. For the 30-degree angle, I believe that I had drawn, it would be a half, right? Sine 30 is 1/2. Again, I recommend that you remember your 30, 60, 90 triangle with all of those particular ratios associated with sine, cosine, and tan, as well as your 45, 45, 90 triangle. G sine theta minus a over 2. Since my m's are gone there, all I'm left with is an a over 2 equals a. Now I'm going to go ahead and throw this equals a. Instead of writing equals a, I'm going to write equals 2 over 2a, because 2 over 2 is still 1, right? So now when I add my 1/2 a to the other side, minus a over 2 and plus a over 2 cancel. And on the right side, rather, I'm left with 2 halves plus 1/2 is 3 halves, yeah? So I have g sine theta is equal to 3 halves times this linear acceleration that we've been after this whole time. And one step more is just to multiply both sides by the reciprocal of 3 halves, which is 2/3. And there you have it. 2/3 g sine theta equals the acceleration. Whether I put a on the right or a on the left, of course, doesn't matter. So it's important to note that g sine theta is recognizable to me, perhaps to you, because when we're talking about something that has no friction, the frictionless ramp, frictionless in this case, if we look at the frictionless ramp and we just slide a block down it, which we talked about a long time ago, and again, here is your mg, total weight, gravity force. There's this y component called FGY. There's the FGX. Remembering that, again, this theta is the same as this theta. And if someone said determine the linear acceleration of the block sliding down a frictionless ramp, since there's no friction up the ramp, the only force parallel to the x-axis, which again goes this way, is FGX, right? And remember, since that's opposite to theta, that's going to go with sine. Format is always the hypotenuse, which in this case, the vector that represents the magnitude of its weight, magnitude of the Earth's gravity force, which again is reminding you it's It's a length. And the format for components is always, the magnitude, the hypotenuse times sine theta or cos theta. You just have to identify, is it opposite to the theta? If it is, it goes with sine. Is it adjacent to the theta? Then it goes with cosine. Right? So now, if we were saying, let's do F net equals ma, you solve for the acceleration. The only net force is mg sine theta. Again, remembering that the normal force that goes in this direction from the ramp cancels with this piece here, which is the y component of the gravity. Those are equal and opposite. So the only unbalanced force, once you have resolved mg, the vector here that goes straight down, once you have resolved that into the two components, then you really have how many things to look at? The normal force, FGY, and FGX. The normal force and FGY cancel, so all that's left is what's unbalanced, FGX. Right? And what do we get for the linear acceleration? G sine theta, which again is recognizable to us in the previous thing that we were just doing. Which again, remember that just means it's a fraction of g. Right? You only get to accelerate at a rate of g if the net force on you, or whatever the object is mg. It's its weight. Surely, if we just use F net equals ma and put in for a falling ball that has no air resistance, the downward force is mg, Earth's gravitational force, then a equals g. Right? That's you only get to accelerate that at that rate when a force, a net force, acts on your body or the object's body, with the net force being equal to whatever it weighs. As long as the net force is equal to what it weighs, I mean, I can accelerate at g sideways. You just have to push me sideways with about 200 pounds of force, and I'll accelerate as a rate of g. If you push me sideways with 400 pounds of force, then I'd accelerate at 2 g's, and so on and so forth. 100 pounds of force sideways on me would cause me to accelerate at a rate of 1/2 g, about 4.9 meters per second squared. So my point is, again, is that the sine theta is just a decimal, right? Sine of 0 is 0, and the sine of 90 degrees is 1, because that has to do with the unit circle, right? As this vector, which we can just start with over here, which has two components, as this hypotenuse that I just drew rotates upwards towards the 90-degree mark, once it approaches this, there's a little x component and a long y component. Once that vector hits the y-axis, the opposite leg, which is this one, is the same exact length as the hypotenuse. They lay right on top of each other, right? Opposite over hypotenuse is sine, and the opposite is the same length. In a unit circle, it'd be 1. 1 divided by 1 is 1. Sine of 90 is 1. Alternatively, of course, if you were to take this vector and rotate it downward, like dropping my ruler, like if this was my meter stick, and I slowly lower it towards the horizontal, then the opposite length gets tinier and tinier, and once the ruler, the vector, actually becomes horizontal, the length of that opposite piece is 0. And since sine of an angle is opposite over hypotenuse, since the opposite is 0, 0 over hypotenuse is 0. Sine of 0 is 0, which means all angles in between there are decimals, right? If those are the two endpoints of this function, then any angle, 10, 20, 30, 40, 50, 60, 70, 80 degrees, they all have to be between 0 and 1, with the sine of 88 degrees being pretty close to 1, but not quite, with the sine of 2 degrees being pretty close to 0, but not quite, a little bit above 0, which is, if it's a decimal, it's a percentage. If the sine of the angle comes out as 0.78, then it's 78%. And that means at that angle, you'll accelerate at 78% of g. Right? You have to start thinking in these ways. Go out of the world of abstract and make sense of it. That's what sine means, percentage. Back to what we were doing, pointing out that the claim is that our disk will actually roll at a rate, linear rate, down the ramp and accelerate at a linear rate that is only 66% of the rate that the other block achieves when it slides down a frictionless ramp. This is not the frictionless ramp. It's rolling. It has to be a frictional ramp for it to roll. Therefore, rolling a disk down a frictional ramp, it will not keep up if it was a race. But now you'd actually have to have two different ramps, unlike before where we were rolling down the same ramp. One ramp has to have friction, the one for this, because if we want it to roll, it has to have friction on it. And the other ramp has to have no friction, like all beautiful ice. The object block is ice, the ramp is ice, it's all ice on ice. So smooth and so beautiful, it's literally no friction. You release those both at the same moment. This disk on the frictional 30-degree ramp against the block on the frictionless 30-degree ramp. Who wins? According to these results, the block is the winner. Not barely either, because the linear acceleration, again, of the block was g sine theta, and this is only 2/3 g sine theta, 66% of that. Why is that? And that's why I'm not going to get into a lot of it now, because that's a whole nother lesson during break. But rotational energy is essentially relating to how rapidly this thing rotates and how much rotational inertia it has. And so when something like a block is sliding down a ramp, all of the potential energy that it has at the top of the ramp, mgh, here's your ramp again, here's your object. mgh is this distance. That's the potential energy, gravitational potential energy, the total mechanical energy, right, of the system. During all points during its trip down, assuming there's no loss of energy to friction. For the sliding scenario, there is some loss, creates heat. Rolling is not a sliding effect. So as long as you recognize that the total potential energy at the top, when you're just something like a puck sliding down, all of that potential energy becomes kinetic energy. And so by your time you're at the bottom of the ramp, it has a kinetic energy, which is 1/2 mv squared, in total amount of joules of kinetic energy equal to mgh amount that it had up here. mgh equals 1/2 mv squared. We've used that. That's old school. Yeah. However, when something is rolling, some of that mgh energy, some of that potential energy that it has stored, some of that mechanical energy, some of it goes into translational kinetic energy. That's the sliding idea that something is moving along a straight line. It doesn't have to be sliding, but it's the idea that it's physically moving along a line. The center of mass is moving from point A to point B. That's called translational kinetic energy. So if I go straight back and forth, this is translational energy. However, if I were to do this, this is rotational energy. The faster I spin, the more rotational energy I have. The slower I spin, the less rotational energy I have. If I stop spinning, I have no rotational energy. But what if I'm going back and forth and spinning while I go back and forth? Now I have two forms of energy. I have translational energy because my body is going in straight lines back and forth, plus rotational energy because I was rotating while I did it. Isn't that what the puck does? The puck is moving along a straight line and rolling while it moves along a straight line. So it has two forms of kinetic energy while it goes down the ramp. Each of them are increasing, but some of that gravitational potential energy, mgh, goes into the translational kinetic energy, 1/2 mv squared, but some of that other amount of mgh goes into the rotational kinetic energy bucket. And that's why this one would lose. It won't, all of the mgh energy that it starts with doesn't turn into pure v speed like it does for the puck. And since it does that for the puck, the pure v speed at the end is pretty high comparatively. For the puck, some of the potential energy again goes into the 1/2 mv, it's the linear velocity squared, but that v won't be as high as before because it's not all of the mgh energy that went into that. Mgh energy gets portioned out into two parts. That's the reason. That's the reason he's the loser. So the mgh potential energy, some of it goes into 1/2 mv squared, And some of that energy goes into kinetic energy, which is rotational kinetic energy. This is rotational kinetic energy. And this is called linear or translational kinetic energy. Again, for going from linear to rotation world, you just take away m and you put I. That's what we did here. And you take away v and you put omega, because those are the analogies for each. But the point is, if this was, 100 joules of potential energy for the puck at the top, for the block that's sliding, the right side is not there. So all 100 joules go straight into this pile, and V ends up being pretty high comparatively. However, when you're referencing the puck that's rolling, if it starts off with 100 joules of potential energy, maybe let's just say 70 joules goes into it moving translationally down the ramp, leaving only 30 joules for the 30 joules to go into the rotational motion. And since in this scenario, the kinetic energy has less amount, 70 joules compared to the full 100 before, the V linear velocity it has must be less because it lost some of that possible energy to the concept that it's rotating, and some of that energy is turning into rotational energy. So rolling down a ramp against something that's sliding down a frictionless ramp, I know, and I have to say the frictionless ramp, because rolling down a ramp against something that actually sliding down a frictional ramp is a different story. And you can clearly see that when I do it right now. I have my ramps already right here. If I were to erase, if I were to erase a washer, I have like a washer, like an actual washer, like you use washers for building things. I'm going to erase this washer against this disk right now. This is not what we just talked about. What we just talked about was a disk rolling down a frictional surface, which is easily achievable here because this has friction, of course. And I can make that happen very easily. However, I do not have a frictionless surface, a frictionless surface. I do not have one of those. Do you? I don't. You have one. Bring it to me. So I can now roll. I'm doing something different. I'm pointing out that if I were to do a real world thing, because nobody has frictionless surfaces, which is a rolling this guy down a frictional surface and racing him against this guy who's going to slide down his own frictional similar surface. Pretty similar, right? And another point is that, yeah, they're not made of the same material. He's made of, it's made of like a pretty similar. I mean, they're not the same material, but they're both fairly hard. They're both fairly smooth. I would guess the coefficients of friction are fairly similar for these two things. So when I erase them, which I think will be challenging for me to, I guess I'd have to put it over here. I now need my meter stick. All right. So I'm going to put my washer is going to go on this track right here. My washer is going on this one. Oop. Actually, I'll just try to do it. I can't because it slipped underneath my meter stick. So I'll have to move my hands as best I can. So I'm going to put my washer on the right side. Here's the washer against a rolling disc on the left side. Best I can, release at the same moment. Not even close. The disc kills it. Not even a race. The disc easily destroys the washer. He says, "Go home, washer. Don't mess with me." So you need to know that that's an important idea. If that was a frictionless ramp for the washer, he would have killed that disk, but that's not what I can do here. The main idea that you do need to know, again, is that when something goes down a ramp, the potential energy, mgh, for the block just turns into pure translational kinetic energy. And it maximizes V because none of its potential energy is being transformed into rotational energy. While for the rotating disk, that's not true. Some of that mgh potential energy is being used. And therefore, the 1/2 mv squared amount is less comparatively. And so he would actually accelerate at a rate less than the other guy, which was g sine theta. In this derivation, it was 2/3 g sine theta. Know that no matter what the geometry is, it's always a fractional amount of g sine theta. If it was a sphere or if it was a hoop, you always get some fraction, 1/2 or 2/3 or 3/4, or you never get g sine theta. Because if they're all rolling, then there's some rotational energy that's being sapped out of mgh, leaving the balance for 1/2 mv squared. So at least you've seen that lesson, because on another lesson, we're going to talk more about modeling what I just talked about, because that might happen on the AP exam. They might say, write down a formula that would model the total mechanical energy of the system at the top of the ramp and at the bottom of the ramp. In fact, is it worth just doing that now? No, take a break. But I will come back to this. It'll be a similar problem. It'll be the ramp. And we can still use some of the old things we used as well before, like V equals R omega. They could ask, what is omega, the rotational speed of this puck at the bottom of the ramp? Or how do you, again, model the whole thing, the mechanical energy as it goes down? We'll do all those things, but we'll come back to this. All right. I'll see you guys later. I'll see you soon. I've got a few more of these to do.